start today a zero address instruction format. So in a zero address instruction format, the CPU organization will be what ma internally it uses which organization? It uses
Stack, ma'am.
this.
Stack
Yes,
organization.
yes, it is a stack organization. So in a stack organization, we'll be using two operations called push and pop. So we'll be pushing the operands, and once an operator, if you get an operator, you will be performing a uh, operation based on top of the stack elements. Okay, and whenever you got a, you will be getting this question, you try to represent stack elements also what you're pushing, and upon an once an operand encounters it top pops the two most elements on the topmost elements on the stack, and it performs whatever operation it is given in the top code, and it pushes the result back in the stack that we already discussed. So today we'll be discussing with one more example for zero address instruction format. So for that, this is the expression which is given. So as everyone knows the priority, so parenthesis will have a highest priority. Next we'll have a multiplication and division. Next you will be having a equal priority. Next you will be having a plus minus with this, which is having a lowest priority. Okay, now I'm starting with this one, where in this will have a highest priority, which is d plus e. Okay, so what I have to do, I need to go for push d. Okay, so push d means what I have to write in the top of this tab, we'll be pushing the operand d. Okay, so along with that you even has to mention the stack as d. Okay, next is what, so you need to push a. So next, top of the stack will be e. So top of the stack will be e. Now you'll be having d, and you'll be having e. Next between this, what operator we have?
Plus.
Plus. So we need to perform add. So it is a zero address instruction format, where for an opcode you're not mentioning any address, simply the instruction format will be simply a opcode. So in this is your opcode where you are given only add. So what happens if you specify only add, it pops the top two elements from this tag, and it performs whatever the opcode it is mentioned. So it is mentioned as add, so it pops e. Next d, so we'll be performing a plus, so you'll be having d plus e. So on the top of this tag you'll be having d plus e. Now represent stack, so stack will have d plus e. Next, coming to, in we'll be having a dot which is multiplication. So what we need to do, so which is multiplication, so in order to
And
do
first
that,
we have
first of all
to
we need to push
see.
c. So we are performing push c, so that we'll be having top of the stack as c. So before this you have a d plus e in a stack. Next you have pushed operand c. Next, there is in between we have a multiplication operator, so you write mul, so the top of the stack will be, c into d plus e. Means what, top two elements from the stack will be popped. Next it performs whatever the available opcode, and it performs and it stores the result back in a stack. Next is what, next step, next is push.
Push B.
Yes, next is push b. So this, until this we completed. So next we need to push b. So I'm pushing push b, and now top of the stack will be b. So previously until here we have c into d plus e. Next we pushed E. Now top of the stack will be C into D plus E will be already available in the stack, and the above I pushed an operand called a B. Okay. Next is what? Next is what?
Add, ma'am.
Add. Yes, add. So we need to perform add. So top of the stack will be B plus C into D plus E. Next, next until
Push
this.
A.
Yes, yes. So next is push A. Next is push A. Now top of the stack will be A. Top of the stack will be A, and this already will be available in the stack. Means whenever we are performing add, top two elements from the stack will be popped. It performs a result and it stores back in the stack. So here you will be having. So here in for this you will be having a top two elements and we'll be getting B plus C D plus E plus C into D plus E. So we popped again in this A. So now A. Next, what operation we have to perform between A and B?
Multiplication.
Multiplication. So multiply, and top of the stack will be what it has. Once if we are giving any op code, then what happens, whatever we have in the stack, top two elements will be popped, and whatever that we mentioned in opcode, that will be performed in between those two operands. So we have one as A and the other one as B plus C into D plus E. So in between we'll be having a multiplication. So A into whatever that we have, B plus C into will be performed, and the result will be pushed again in a stack. So this is a result which is available in a top of the stack now. So you can represent that with this. This will be available here. Okay. Next step is what, ma'am?
Store T.
No, no, no.
No,
Okay.
ma'am. Push G.
Yes, see ma, I want to give one information. So whenever we are using zero address instruction, keep it in your mind that we'll be using only push and pop. Okay, we'll be using only push and pop and an opcode, and the opcode in between, so that it performs a particular operation. Whenever you are discussing about zero address instruction format, we'll be using only push and pop, and whenever we are discussing about one address instruction format, we'll be using what, ma? Can anyone? One address instruction format.
Accumulator.
Yes, accumulator means we'll be using which
Load and
instruction?
store.
Yes,
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 ma'am.
good. So if it is one address instruction format, we'll be using load and store. And if it is a three address and two address instruction format, we'll be using for three
Ge-
address
General register, ma'am.
general registers means I'm asking the instructions that we are using. We'll be using
Move.
add, move, like that, add, move, like that. Okay, so whenever you will be getting in any exam questions, this type of a questions, keep it in your mind that if it is zero address instruction, we have to use only a push and pop. If it is one address instruction format, we need to use load and store. If it is three address instruction format or two address instruction format, we need to use move, addition, subtraction, like that. Okay, so now we are in a zero address instruction format, we should only use push and pop. So here now this we have here a this one. Okay, next is what we need to perform this operation. Okay, why? Because this is in a parenthesis, so I have to perform this one first. So I have to push G, so that in the top of the stack you will be having G. Next is what, ma? Next push
H.
H, so that the top of the stack will be H. Next, in between, what operator we have?
Addition.
Addition. So perform add, so that we'll be having top of the stack. I'm not representing the diagram, but you need to represent. So G plus H. Next is what we have to do? Push.
Push F. F, ma'am.
Yes, we need to push F, so the top of the stack will be F. Next is what?
Multiply.
Yes, mul. We need to do mul. Now, top of the stack will be G plus H. We'll be having one more operand in our stack as F. Both will be performed. F into G plus H. Next step is what, ma'am?
Division,
Next,
ma'am.
yes, div means what? One in one side, you one in one you'll be having this one, and the other one you'll be having this one. So between this, we are performing a division operation. So now top of the stack will be what the expression is. Okay. So in this way, we'll be using a zero address instruction format for, but for every instruction, keep it in your mind that you need to represent the stack diagram. Okay. And this is your zero address instruction format. Now let me explain for three. Just let me just give me a timer so that everyone noted in your notes, ma. It's completed.
Yes, ma'am.
Okay, I'm clearing. So I will go for clear all and I will write the expression again. Okay. So now let me start with three address. So what I said yesterday about three address, ma? Three address instruction format advantages and the drawbacks of three address instruction format. The advantages.
Short programs.
Yes, instructions what we are writing for that particular expression in three address instruction format will be number of lines will be less, but when compared to an instruction format, the as we have three address, the number of bits will be increasing. So that's a problem in a three address instruction format. So I want an answer, ma, please. So we for every instruction format, you need to check up about operator precedence, and if you have an equal operators, we need to go for associative rule. Means if you are having in this like b divided by f into g, then what you have to do, multiplication and division will have a equal priority. Then you need to go for associative rule, where it gives based on an operator whether we need to evaluate from left to right or right to left. So this you need to evaluate from left to right. So based, you need to think about the operator precedence rules, and if you are having an equal priority, then even we need to go for associative rule based on an operator whether it has to evaluate from right to left or left to right. Okay. Now let me start with three address instruction format. So in three address instruction format, we need to do this first. Okay. So first instruction, can anyone?
Add R1D.
Add, just a minute. Add, we need to get three. So whenever you are trying to write a instruction for three address simplification, so you should think about, you should get three address. So one is R1. So what I want to do is I want to go for memory location D, and I want to get the data and this, and I want to perform an addition, and the result I want to store inside an R1. So D comma E. Okay. So what does this indicates? Tell me the answer ma in R1.
R1 D plus E.
Yes.
M of
So
M of
M
D
of
plus
D
M of E.
plus M of E. Okay. M of D plus M of E. Next.
Mul R2 comma C and R1.
Just for sake of understanding, what I'm doing is, so in R1 we'll be having D plus E. Okay. Now let me write mul. Next step is mul. We need to do multiplication. Why? Because in this part is completed. Next is C. Okay. So multiply.
R1 and C.
Yes. R1 and C. So that I want to take which register?
R2.
Yes, R2. So
R2,
I want to
R1, C.
store, yes, R1. I want to store the result in R1, and one result is available in R1. So which is D plus E. So R1, and the other one is we need to go to a memory location C. So whereas in R2 we have now R1 into M of C. M of C. If you know, you can note down in your notes, and you can tell the next instruction. Next is what?
Add, ma'am.
Yes, add. Okay. So add. So add means what will be available. One operand we need to go to memory location, and the other operand, this entire is present in C
R2.
into D plus E is available in register
R2.
R2.
R2. Okay. Now please answer. Should I take R3 or should I take R1? Which register I need to go for, R3 or R1? Is there any need of this D plus E now?
No, ma'am.
No. So D plus E into C, the entire result combined and then stored in R2, right? So I can override the data, means D plus E not needed. So should I take now R3 or R1?
R1.
Yes, very good. So why? Because whenever you are using a general purpose registers, what we have to do is we need to minimize that. So we should not take unnecessarily a more number of general purpose registers. What happens internally when it is doing is it slows down the system. Why? Because general purpose registers will only be available very less. So if you are using for unnecessarily storing the data, for the next instruction to utilize those registers, it will become not available. So your that indicates your system will slow down. So whenever it performs it internally, a system, it try to use the one which it has to use. Okay. So we are using R1 now. So R2 comma what operator?
B.
B. Means what we have to do, in R1 we'll be storing R2 plus M of B. M of B. Next is what?
Multiplication.
Yes,
Mul.
multiplication. Mul. Now which register I have to take?
R2, R1,
Yes, very
A.
good. So R2 now it is no more needed. Why? Because in R1 we have this entire data in R1. So we can take now R2 comma R1 comma A. Okay, where in R2 you have the entire numerator result, where R1 multiplication, we are multiplying with a memory location A. You should even draw the diagrams. It should say that we have a memory where you are going to that memory location and you are getting the data, and you need to analyze register R1 with some value, and whenever it is performing the result of that value, you should get 30, like that. You should explain with a, after completion of this, you should take the values for A as sum. I mean, you need to go to that location and you need to explain so that you can score maximum marks. Next step is what? So now this entire numerator result is present in which register, R1 or R2?
R2.
Now
R2.
it is present in R2. Next step.
Add.
Yes, we are performing add. Why? Because this parenthesis will have a highest precedence. So now which register I have to take?
R1, G, comma, H.
Yes, R1 G comma H. Means in R1 register we are going for G address location and we are getting the data, H address location and we are getting the data, and we are performing an addition. We are performing M of H, we are performing an addition, and the result we are storing in R1. Next is mul. Mul. Should I use R2? Should I
No,
use
ma'am.
R2? No. Why?
No.
Because R2 we have the numerator result. Now I have to take which register?
R3.
R3 comma R1 comma
F.
f means the in R3 we are storing R1 plus m of f. Next
Into 1.
operator. Yes,
R1
into.
into
Yes, this one is into. Okay. Next operator.
Division.
Yes, division. Now I will see who will answer. Division.
X.
The above numerator is available in R2. The denominator is available in which register, ma?
R3.
Yes.
R1 comma R2 and comma R3.
X
Can
comma
anyone?
X comma R2 comma R3.
Yes, very good. So instead of placing that inside a register, it is mentioning that you store the result in X, no? So there is no need of using one more register. Simply you can mention the result and it has to be placed in a memory location X. So X comma R2 comma this one is available in R3. So R3 means what? In memory location M of X, you need to assume some address, and in that address it stores R2 divided by R3, and the result will be stored in a memory location M of X. This is three address instruction format where the number of instructions will be less, but the complexity is the as we have three address, the opcode followed by you'll be having the number of bits more. So you'll be having an opcode and address 1 and address 2 and address 3. So advantage is the instruction length will be less when compared to number of bits will be increased. Now let me go for the other one which is left is which one, ma'am?
Two address, ma'am.
Yes, two address instruction format. Now I want the remaining students to unmute and answer, ma'am. So two address instruction format. Okay, tell me the first instruction what we have to do. So whenever you are writing about two address instruction format, think about you should have the instruction type as opcode, address 1, address 2. What we have to do?
Move R1 comma D.
Yes. The first step is move R1 comma D means what? Inside a register R1 we are going to memory location M of D, and whatever the data which is available in that we are placing inside a register R1. Next,
Add R1
add.
comma D. EE.
Yes, very good. Add R1 comma E means what? Inside a register R1 we have already D. Okay, so again we are going to memory location E and we are getting the data, and in R1 we have a D and we are performing addition with memory location in that what data is available, both we are performing an addition and the result we are storing back in R1. So in R1 we have, so in R1 we have D plus E. D plus E. Next. Next is what, ma'am?
Mul
Move
R1 comma C.
Yes, very good. Okay, so mul R1 comma C means in R1 you already have in R1 this D plus E. For that you are doing multiplication based on the expression which is given. So R1 into M of C. Next,
Add R1 comma B.
yes, add R1 comma B, where in R1 we have now what is available in this R1, ma? C into D plus E is available. Now with this we are adding memory location B. Okay, so R1 plus M of B. Next,
Mul R1 comma A.
Yes, mul r1 comma a means in r1 until here we have r1 as b plus c into d plus e. Now we will be having in r1 this one b plus c into d plus e plus we need to go for memory location a, so that we'll be performing. So in r1 what will be present in r1?
Numerator.
Yes, in r1 we have a numerator. Next,
Move R2 comma G.
yes, move r2 comma g. Next, add
R2 comma H.
r2 comma h. So what is this? In r2 we are placing memory location contents g, whereas in this in r2 whatever we have in an r2 along with that we are adding what we have in a memory location m of h. Okay, next is what? Mul. Next mul.
R2 comma F.
Yes, mul r2 comma f means in r2 we have until now we have g plus h. Along with that we need to go for memory location and we need to perform multiplication. So r2 into m of f. Next,
Division. Div R1 comma R2.
yes, div, we are dividing the r1. In r1 we have a numerator and in r2 we have a denominator, and the result I'm storing back in register r1. So r1 divided by r2. Finally,
Move x
Move
comma
X comma R1.
yes, I thought that anyone will say a store. Okay, store and load will be used only in one address instruction format. So finally we have to use move x comma the result is available in register r1. So finally in memory location m of x we are storing the register r1 contents. So in this we have this expression. Okay, this is your one address